Hello, I'm Chu Chen. I'm going to present our paper, FEJ2, a consistent visual-inertial estimator design. In this work, we are addressing the consistency of filter-based visual-inertial estimator. From observability perspective, an ideal winds should have 4 unobservable directions, corresponding to global yaw and position. But the standard EKF, which linearizes at the currency estimates, makes the global yaw to be observable, and causes the filter to gain extra information, thus become overconfident and inconsistent. As shown in the top figure, the green line represents the standard EKF. The NES grows to a large value. It means the estimated covariance did not capture the true uncertainty, and we can see this directly impacts the accuracy as it increases estimation error showing the RMSE plots. The first estimate Jacobian method fixing the Jacobians at the first estimate. This prevents information gain along with unobservable directions, but can introduce errors if poor initial estimates are used. In this work, we carefully model the extra errors that FEJ could have and propose FEJ2, which is shown to improve performance. As shown in the figure, FEJ2 achieves even better consistency and accuracy than FEJ. In order to understand FEJ2, let's start with a typical nonlinear measurement function. We use Z to represent the sensor measurement. H is a nonlinear measurement function. X is the state vector we want to estimate, and N is the measurement noise. Following the first order Taylor series expansion, the measurement function is linearized at the currency estimate, X hat. The corresponding Jacobian is H hat. After this, we can perform EKF update, which will result in an inconsistent estimator. FEJ evaluates the measurement Jacobian at the first estimates, represented as H bar in our equation, in order to improve consistency. However, we notice that by directly changing this Jacobian, the resulting linearized equation does not strictly follow the first-order Taylor series expansion. After 2 more steps derivations, it is clear that FEJ ignored delta H in order to improve consistency, but it could introduce unmodeled errors. In FEJ2, we carefully consider delta H, since it captures the differences between Jacobians evaluate the first and currency estimate. A general consideration is it could represent the linearization errors. In addition, since H bar ensures the system observability properties and H hat do not, delta H thus could causes the extra information gain. For these reasons, we get rid of delta H by projecting the linearized equation onto its left non-space, delta U. We then perform EKF update using the resulting equations. At this point, we see FEJ2 is a more consistent and accurate estimator, which guarantees the system observability properties and better models the uncertainty. We have implemented FEJ2 into different bins framework. In the simulation, we test both monocular and stereo cameras with different noise values. In the table, we show the simulated noise are either 1 or 3 pixels. FEJ2 is compared against the standard observability constraint and FEJ wins. It is clear that FEJ2 outperforms the others as it achieves the lowest RMSE and the most ideal NES, especially when the measurement noise is relatively large. In summary, we develop a novel consistent wins estimation algorithm. The proposed FEJ2 accurately models the potential errors that FEJ ignores and achieves better performance. Thanks for listening.